Hello, y'all. This is a review for specifically my AP Calculus kids as they prepare for their Unit 6A test. So this is basically a test over left and right hand midpoint trapezoid Riemann sums, so approximating areas under the curve, and then some antiderivatives and some integrals. So actually taking integrals. So we're going to take a picture of a problem, and then we'll do the problem together, and then take a picture of another one, and then we'll get it all done. So hopefully this won't take very long, and it will be beneficial to your understanding. So in this first problem, we're given that we are defining, right, some function called f from a to b as being this answer. So we want to know what happens if we add 5 to it. So we're going to use our properties of integrals and break this into the sum of two integrals. So from a to b of f of x plus, that's a plus, from a to b of 5. Okay, well we already know what the answer to this is. The answer to this is a plus 2b. And we take the integral from a to b of 5 by multiplying, right, by anti-deriving. So we're going to take the antiderivative, so we're going to multiply it by a variable. And we're going to evaluate that variable from b to a. Okay, so once again, this part is going to be 5 times b minus 5 times a, right? That's how we evaluate an integral. Plus, we have this other stuff over here. So now it's just a matter of combining my like terms. I have a 2b and 5b, which is 7b, and I have in positive a and minus 5a, which is minus 4a. So 7b minus 4a gives me an answer of C. Okay, on to number 2. So here we have a table of values. We want to make 4 equal subdivisions using the trapezoid method. So the area for a trapezoid is 1/2 of the left base plus the right base times the height. And the height is the distance in between your two bases. So your bases in this case are your y values, because our trapezoid is going to be a vertically oriented trapezoid. So we have the bases that are the y values, and the height is going to be the x values, or the distance in between your bases. Okay, so we can approximate this by doing 1/2 of the first base, which is 3, plus the second base, which is 3, times 1/2. That's the distance in between 0 and 1/2. Okay, we're going to do the same thing for all of these. So 1/2 of 3 plus 5 times, once again, 0.5, plus 1/2 of 5 plus 8 times 0.5, plus 1/2 of 8 plus 13 times 0.5. Okay, so when we're using the trapezoid method, every one of these numbers, except for the first one and the last one, is used twice because it's a trapezoid, right? And we need a left side and a right side in order to have a trapezoid. So whenever we make our next trapezoid, we use the right hand from the first one, right, and then the next point. So make sure that this is what you're doing when you're doing a trapezoid method. You have to use both the left side and the right side. Okay, and when we do that, we come out with 12 as the answer. So make sure you can add together and divide properly to get the answer of 12. Okay, number 3. So this one wants us to use a right Riemann sum. Sorry, I got to get my pen out. A right Riemann sum with 3 subintervals. So we're going to start at 15 and make our rectangles coming backwards. Okay, so we're not going to use the 6.5 as the height. In fact, I like to do this literally working backwards from right to left. So this integral is approximately the right-hand endpoint of 5.6, right, times a width of 3, plus the next right-hand endpoint of 5.9 times a width of 5, because 7 to 12 is 5, plus the next right-hand endpoint of 6.2 times another width of 3. Okay, so we use this endpoint right at 5.6, and this is our width moving from right to left, if you want to use the right Riemann sum. Okay, now this comes out to be approximately 64.9 liters of oil. But it said we were initially had 50 liters to begin with, right? So we can't discount our 50. We have to make sure that we add that in because it wants the total liters of oil that are in the tank. Right? So this is a rate of oil going into the tank after 4 hours when there were 50 liters to begin with. So we have to add our original 50 liters to our 64.9 liters, giving us 114.9 liters of oil after 15 total hours. Okay, on to number 4. So here we have a graph of people standing in line for a certain ride, and there are 275 people at the beginning. So just like last time, we have an initial quantity. So we're going to have our 275 plus whatever the integral is from 0 to 4, okay, of our graph of people standing in line at a given time t. So this looks like a great time to have well, it just looks like right, we're going to find the area under the curve. So I'm going to make 2 shapes, right? Number 1 shape is a trapezoid. Okay, so we're going to make a trapezoid because that's what really fits this graph really, really well. It looks like a trapezoid. So 1/2 of the left, which is 1,000, right? That's the height of the left side, plus the height of the right side, which is 1,200. And it has a height of 2 hours. Plus, I'm going to make another trapezoid here. All right, so 1/2 of my left side, which is 1,200, plus the right side, which is just 400 people, times, once again, my height, which is 2, so 2 hours. Okay, so I'm using a trapezoid method because that's what fits this graph really well. It looks like a stinking trapezoid. So if we take our 3 numbers, 275, and this one, the 1/2 and the 2 cancel out and give us 2,200, and this one, the 1/2 and the 2 cancel out, give us 1,600, that gives me 44,075 people that have been waiting in that line over those 4 hours that the park has been open. Okay, so make the best geometric figure that fits the graph. So in this case, trapezoids. On to number 5. So here we're asked to find the value of an integral of a sum of 2 functions, right? So we have 2f prime plus 3f double prime. Okay, so once again, we can use that property of integrals and break this into 2. Oh, that's not what I want. I want my f to be normal. So 2f primes plus the integral from -3 to 1 of 3f double primes. Okay, so now I'm going to take the antiderivative, and the antiderivative of 2f primes is 2f's, right? So 2f of x. And nope, I am doing this wrong. I do not need to have the integral symbol anymore. Okay, in fact, I want to evaluate this from -3 to 1, and then plus the antiderivative of f double prime is f prime. And I'm going to evaluate that from -3 to 1 also. Okay, so I'm going to do this up here because I'm going to need my values. So I'm going to take this, I know it's not space-wise. So this is 2 times f of 1 minus 2 times f of -3. Okay, so that's how you evaluate it from 1 to -3. And then plus 3f primes at 1 minus 3f primes at -3. Okay, now these values are coming from our table, okay, which is why I wanted us to see the table here. So 2f of 1, f of 1 is 7, minus 2f of -3 is 7, plus 3f primes at 1, so f prime at 1 is 5, minus 3f primes at -3, which is -5. Okay, so we basically have here 14 minus 14 plus 15 plus 5. And And I've noticed that I've made a mistake. I need to multiply this in here by 3, don't I? So this one needs to be minus 3 times negative 5. So 15 plus 15 comes out to be 30. There we go. That sounds better. I was wondering why my answer didn't look right. Okay, so you take the antiderivative and you lose, right? Oh, you lose a prime. So the antiderivative of f prime is f, and the antiderivative of f double prime is f single prime. Okay, on to number 6. Okay, so this is just taking an antiderivative of a polynomial. So the rule is when you take an antiderivative of a polynomial, you add 1 to the power and you divide by that new power. So we're going to have 2x to the 4th power divided by 4 minus 3x to the 3rd power divided by 3 plus 4x to the 2nd power divided by 2 plus 1x to the 1st power divided by 1. Okay, so if we really want to be extra, we can write that in there. And then there's some plus c value, because when you take the derivative of a constant, it goes away. So when we're anti-deriving, make sure that we just add in that plus c to remember that there can be a number there depending on the initial condition. So now we'll simplify, and this will be 1/2 of x to the 4th minus x to the cubed plus 2x squared plus x plus c. And it looks like that answer is right here, letter A. Okay, just an antiderivative of a polynomial. Right, on to number 7. So number 7 starts to read like it would be one of our value theorems, right? Continuous on the closed interval. And we're given some, so let's draw our interval. Here is an interval. Here is A, right? Here's our interval A, and here is B. So we're assuming that A is less than B. It's an okay assumption. So then we have -3 as the y value that goes along with A, and +8 is the y value that goes along with B. So since it's a continuous function, the graph has to do something as it goes from -3 to 8. Okay? So we know by the intermediate value theorem that all of the y values between -3 and 8 will be covered. Okay, for sure, because that's what the IVT guarantees. So we don't know if it's going to go above or below. So what statements are true about the open interval? There must be a c where it's -4. Okay, and that's not okay, right? They could be, -4 is down here, but the graph does not have to go down before it goes back up to 8. So part 1 is not necessarily true, right? Not guaranteed. Could happen, sure, but does not guarantee it. Number 2, must have at least one 0. Sure, it must cross 0 to get from -3 to +8. And the limit exists for all values. Yes, that's the definition of a continuous function. So our answer are part 2 and part 3. Okay, so this is just a value theorem. Do you understand what it is asking you to do? Okay, on to number 8. So we're finding the limit as x goes to infinity of this polynomial function. Okay, so if we plug in infinity everywhere, we get infinity over infinity, which is an indeterminate form, right? So we can apply L'Hopital's rule and take the derivative and then check it again. And you will see after we do this so many times that we're going to come out with a function that just focuses on these two highest powers of x. Okay, x to the 5th and x to the 5th, everything else will basically go away, and we're going to be left with our coefficients, which are +2 over -3. Okay, so this is also from pre-calculus. Notice that this is a neutrally heavy rational function. So if it's a neutrally heavy rational function, the limit as x goes to infinity is found by looking at the coefficients of your highest powers of x. Okay, so you could either do L'Hopital's rule with a bunch of derivatives, sorry, or remember your pre-calculus. On to number 9. So in number 9, we have defining two integrals. Here we have from 4 to -10 is this answer, and then from 4 to 6 is this answer. And we want the integral from -10 to +6. So we're going to break this negative 10 to positive 6 up into the sum of two smaller integrals. So from negative 10 to 4, right, because we're given a value for that, and the integral from 4 to 6 because we are given a value for that in our problem also. Okay. Now this one we're not exactly given, right? Something similar to this we were given from 4 to 10, and this is from negative 10 to 4. So what happens, I hope you remember, is that when you switch your limits of integration, right, the top and the bottom switch, then the area under the curve becomes negative. So if we're going to go from negative 10 to 4, that's going to be the negative of negative 3. Okay, when you switch your limits of integration, the area becomes negative. So we went from negative 10 to 4, which is the negative of the thing that we were given. And from 4 to 6, that's normal, just positive 5, so we get a total area of 8. Okay, so this is applying some of those properties of integrals that we studied in class. Okay, on to number 10. Okay, we're given a chart of tables and want to find the value from 1 to 3 of f prime. So remember, when we're taking the antiderivative of a derivative, the answer is just the function itself. So f of x, and we're going to evaluate that from 1 to 3, or from 3 to 1. So that's f of 3 minus f of 1, right? This is the fundamental theorem part 1, is how we would write this. Fundamental theorem part 1. So that means you take f of 3, which is 0, minus f of 1, which is negative 4, and 0 minus negative 4 is positive 4. Okay, not too bad taking antiderivatives. All right, number 11. Actually, we're going to do 11 and 12 together since they are basically opposites of each other. Okay, so we can take our limit of integration from a to b of some function, and we can write it as the limit as not x, but rather n goes to infinity of a sum of rectangles, right? So we're going to start with one rectangle, and I don't know how many rectangles I'm going to end with, so from 1 to n of this really funky function. So we start with the lower limit. Okay, so the lower limit of integration, right, comes in here to begin, because it's important to know where we start, plus what we call delta x, right? And these are the widths of your rectangle, the x coordinates for your rectangle. How wide are we choosing? And we're going to figure out how many of rectangles we're going to make. So delta x times I, right, our subscript, and then we're going to multiply it by the heights. Remember, the heights are, well, actually, let me get this right. These are the heights, right? These are different y values. So those are the heights. And then we're going to multiply it by the, the width again, delta x. Right, so these are the widths of your rectangle, delta x, where the y values are the heights, right? Your f of x stuff is the height. Now there's an important distinction. The delta x is found by taking the width of our integral, right? We're going to divide it into I don't know how many subparts. So we have b minus a, that's the width of your whole entire interval, and we're dividing it into n rectangles. Okay, so that's going to go into here and here. So let's see if we can make sense of that with our given problem. Okay, so we have from 0 to 5, right? So we have, all of these have the same limits, right? Oh, this one starts at 0 and that one starts at 0. So let's throw those out. Those don't look like they match our 1, because we wanted to start at 1, right? We're starting at 1 almost always, so we can throw away b and d. So the sum from I equals 1 to n of a, which is 0 plus delta x, b minus a. So 5b minus a for our problem is 5 minus 0, which is just 5. So 5I over n times 5 over n, right? That b minus a again. Oh, I forgot about the plus 1 part. Let me squish that in here. Pause. There we go. I took the whole function and put it in here. There. Now I've got it. So we end up with 5i over n plus 1 times 5 over n. So it looks like the answer here is going to be C. Okay, and now we're going to go backwards. Right, backwards. So notice I have a plus 5 for number 12. We're going backwards. Plus 5. So let's see, that's part of our function is the plus 5. And then we have something being squared. So that must be our x squared part, right, dx. Now we have to figure out our limits of integration. Our lower limit comes from this number right here. So that's a 1. Okay, and we know there has to be an interval of 2, right? So if the 1 is your a value, that's not the right way to write it. B minus 1 has got to equal 2, then b needs to equal 3, right? Because it has to be 3 units, or rather 2 units is our interval, and we're starting at positive 1. So the interval from 1 to 3 of x squared plus 5 dx. And that answer looks like it's here at B. Okay, so you're just going to have to memorize that formula, right? Memorize it, memorize it, memorize it. Write it down again, and then write it down again until you have memorized it. Okay, number 13. So we're ending with an initial value problem. Okay, so we want to write a whole entire function if we know that the second derivative is x squared, that we have, right, when x is 0 on the first derivative, y is 6, and then when x is 0 on the second derivative, y is 3. Okay, so we're first going to start with the second derivative, right, exactly where we want to go is x squared, and then we're going to take the antiderivative of x squared, which is x to the third power divided by 3 plus some value c. Okay, now we're going to use our initial condition. We know that the y value is 6 when our x value is 0. Okay, so we use this information to figure out what our c value is, and it looks like c is going to be 6. Okay, so our first derivative comes out to be x cubed over 3 plus 6. And now we take the derivative of that, the antiderivative of that, which is x to the 4 over 3 times 4, right, because we have another denominator, plus 6x to the first power over 1, which is just dumb, plus some value c. Okay, so our function is x to the 4th over 12 plus 6x plus c. And now we know that the y value is 3 when x is 0. So we put a 3 here and a 0 in for all of our x's. Okay, and that gives us a c value of 3. So our final function looks like x to the 4th over 12 plus 6x plus 3. Let's see if that's an option way up here, really small. 1/4 6x plus 3. Yep, looks like the answer is A. Okay, so this is how we use our initial conditions, right? The y value goes here and your x value goes there. So the x is always in your parentheses. That's what your x value is. Okay, so when they give it to you, this is your x value and this is your y. This is your x and this is your y. Okay, now the last thing that we haven't talked about, and there weren't any problems, is the second fundamental theorem. Okay, so if f is the integral from a to some function, right, and this was a variable, usually x or x squared or something, of an antiderivative, then we could find f prime simply by replacing the variable in your function with that upper limit, right, your upper limit of integration, in this case variable of integration since it's going to change, times the derivative of that variable up there. Okay, and we did various problems with this in class. So there weren't any on this review, but I'm pretty sure there's going to be some on the test. Okay, so hopefully this is helpful, and you feel confident that you can do fantastic on the test tomorrow. Have a great day.